I, Mrs. K.S. Gadgil from Department of Electrical Engineering, AISSMS IOIT Pune, today is going to discuss first order low pass Butterworth filter. Let us see at the circuit diagram of the low pass Butterworth filter. We will see that here the elements R and C network are used for what? They are used for filtering, and the op amp is used in the non-inverting configuration. Non-inverting configuration means we are giving the input signal to the non-inverting terminal, right? And it does not load the RC network also. Then the resistances R1 and RF. The resistances R1 and RF determine the gain of the filter, right? Now before proceeding for the analysis, we need to find out the potential V1 at this point, right? If you see this part of the circuit, that is your V in, the resistance R and the capacitor, form a voltage divider arrangement, right? So if you find out the impedance of the impedance of the circuit becomes what? R minus jXC, right? So the current is going to be what? V in upon R minus jXC. We need to find out the potential across the capacitance C. So we are writing V1 will be equal to what? Minus jXC upon R minus jXC into V in. We know that j is equal to minus root 1 and minus jxc is equal to 1 upon j 2 pi fc. You have what? Minus jxc is equal to what? 1 upon j 2 pi fc. Now if we substitute these values in the previous equation, minus jxc is what? 1 upon j 2 pi fc. So we are going to substitute that over here. So you get it as 1 upon j 2 pi fc into the bracket r plus, it was minus jxc over there. So minus jxc is nothing but what? 1 upon j 2 pi fc, the whole into V in. So you get what? V1 is equal to V in upon, this is going to get cancelled when you multiply, and you get it as what? 1 plus j 2 pi f RC, right? Now since the op amp is in the non-inverting configuration, you have output voltage V0 is equal to 1 plus RF upon R1 into V1. What is RF upon R1? You have RF and you have R1 over here. So the output voltage is given as V0 is equal to 1 plus RF upon R1 into V1. We will substitute the value for V1. So you get V0 is equal to 1 plus RF upon R1 into V in upon 1 plus J 2 pi F RC. Right? Now we will rearrange these terms. If I rearrange, I will get it as what? V0 upon AF is equal to AF upon 1 plus J into bracket F upon FH, where V0 upon Vin is a gain of filter as a function of frequency. What is AF? What is AF? AF is 1 plus RF upon R1. What is AF? 1 plus RF upon R1, which is the pass band gain of the filter, right? F is the frequency of the input signal. What you have in the terms over here? You have 1 plus J 2 pi F R C. So here F is what? F is nothing but what? F is your frequency of your input signal, and you have what? FH. FH is nothing but what? 1 upon 2 pi RC, which is called as what? High cutoff frequency of the filter. It is called as what? It is called as high cutoff frequency of the filter, right? So this is how we have come. We started with what? We started with the simple circuit for a Butterworth filter, where we have configured the op amp in the non-inverting mode. Then we have connected R and C elements as the filtering elements, or the filtering elements, correct? Then we have written the potential at point V1 using the voltage divider rule. Then we have rearranged then we have written the output voltage of the op amp. Since it is in non-inverting mode, we have written it as what? V0 is equal to 1 plus RF upon R1 into V1. Then we have substituted the value of V0, then we have substituted the value of V1 over here. We have rearranged the terms, and we have come to the conclusion of V0 upon Vin is equal to the gain of the filter as a function of frequency. Then you have AF is equal to pass band gain of the filter. F is the frequency of input signal, and fH is equal to 1 upon 2 pi RC is the high cutoff frequency of the filter, right? Now this is how you have come to the higher cutoff frequency of the filter. The gain magnitude and the phase angle equation of low pass filter can be obtained by converting the gain into the equivalent polar form, right? So we can convert this into an equivalent polar form and you can find out the magnitude, right? You can find out the magnitude as V0 upon V in is equal to AF under root of 1 plus F upon Fh square and phi is equal to minus tan inverse of F upon Fh. This can do from conversion from the to get into the polar form, the frequency and the phase angle in the polar form, right? Then you go ahead. Let's see the operation of low pass filter from the gain magnitude. Now, if you have seen the gain magnitude, it is what? AF upon under root of 1 plus F upon FH the whole square, right? Now, we are going to see three steps for finding out the operation of the low pass filter and we will see the frequency response of the low pass filter simultaneously, right? Now at very low frequencies, that is f is less than fh. So if you see if f is less than fh, then f upon fh the whole square, a smaller number divided by a larger number is small, so the square is also small. So ultimately you get what? V0 upon Vn is equal to what? AF. You get V0 upon Vn is equal to what? AF. Now, if you take, this is for lower frequencies, right? You will see that at lower frequencies. So from um, 0 hertz to, let us see what happens at FH. If you see at FH, what happens at FH? If F is equal to FH, so FH upon FH is going to become 1. So 1 plus 1 is going to become 2. So you get it as what? AF upon under root of 2. Right? You get it as what? AF upon under root of 2, which is nothing but what? 0.707 AF, which is nothing but what? 0.707 AF, right? So what you can see is that for a low pass filter, it has a constant gain of AF from 0 hertz to high cutoff frequency, right? At FH, right? So you can see over here, it from 0 hertz to high cutoff frequency, it has what? It has almost the constant gain. At FH, the gain becomes what? The gain becomes 0.707 AF. And F after FH, sorry, when F is greater than FH, when F is greater than FH, the gain becomes what? The gain becomes less than AF. It starts decreasing. It starts what? It starts decreasing. So, and it decreases with a constant rate with increase in frequency. That is, when you increase the frequency tenfold, the voltages gain is divided by 10. That is, the gain decreases by what? 20 dB. That is why you have written as was minus 20 dB per decade, right? So, so in other words, you can say that the gain decreases 20 dB each time the frequency increases by 10, right? So this is how the frequency response is of the low pass filter. For what you have is that up to FH the gain is almost constant as AF. At FH it is 0.707 AF and after FH it starts decreasing. So this band is called as what? This band is called as the pass band, and the other, when it goes at f is equal to fh, the gain of the circuit becomes decreases. That is why it is called as what? It is called as the stop band, right? So fh is called as the cutoff frequency because the gain of the filter at this frequency is down by 3 dB from 0 hertz. What are the other terms which are used for the cutoff frequency are the minus 3 dB frequency. It is also called as break frequency, or it is also called as what? Corner frequency. So low pass filter means what? It will pass all the signals which are having frequency less than the lower cutoff frequency, that is what? FH, and after FH all the signals are there is going to be decrease in the gain as the frequency is going to increase. So this is what we are had to share about the low pass Butterworth filter with you all. So what we have seen is the circuit, where you are using RC elements as the filtering elements. Then you have configured the op amp in the non-inverting mode, and we have seen the frequency response. You have three stages for the frequency response. One is the frequency is less than FH, where FH is your cutoff frequency. At that time, the gain is almost constant, which is AF, the frequency AF. Then at F is equal to FH, the frequency is 0.70 F. And as the frequency becomes greater than FH, the gain of the filter circuit starts decreasing. That is why it is called as the stop band. And all frequencies below FH are going to pass through the circuit. So it is called as what? It is called as a low pass filter. This frequency also has different names as minus 3 dB frequency, break frequency, or corner frequency. So this is what I wanted to explain today regarding the low pass Butterworth filter. Thank you.